All right. Hello, y'all. So we're going to be doing some paper two and paper three questions. I'm just going to walk you through them. I'm kind of just go. So if you are trying to solve these ahead of me, which I highly suggest you do, please pause before I start going over the answer. So I'm going to read the question and then I'm going to jump right into how to do it. So pause and try them on your own pace. Otherwise, watch this at one speed, one and a half, two times, whatever it makes, so that you can understand what you need to understand while not taking up your entire time. So with that said, I'm doing questions 7, 8, 9, and 10 from the homework, and we're just going to jump right into it. So for question 7, define the term standard enthalpy of formation and using methanol as a compound formed, write an equation to illustrate the definition. So we have two parts here. So the first part is the standard enthalpy of formation, which we've done this many times. It's the change in energy required to produce 1 mole of a substance. And then we usually talk about this in standard state, so in standard conditions, which you may remember as either 298 Kelvin or 25 degrees Celsius or 100 kilopascals or 1 atm. I'll be honest, the IB likes these top two more than they like the bottom two, so you can just stick with that. So that is part one. That'll get you some points. Part two is a little trickier. They're asking for methanol as a compound formed. Write an equation to illustrate the definition. So we need to write a chemical equation that shows the formation of methanol. Well, we can see from later that methanol is this if you haven't yet learned organic chem, or I haven't taught you that yet. So we are trying to form CH3OH. And we talk about this from the basic elements. So that might be something good to have in here. So this is from basic elements. Now, the elements I see in CH3OH is carbon, hydrogen, and oxygen. Now, the problem is, while carbon comes in a solid state, hydrogen comes in a diatomic gas state, oxygen also comes in a diatomic gas state. So we have to figure out how to balance this. Well, we only need one carbon, so carbon's going to stay as is. We need two hydrogen to balance out the 3 plus 1, the 4 hydrogen. And for this, because we're just making an example, you don't need whole numbers. You can just do 1/2 oxygen. And it's actually required that you do 1/2 oxygen. And the reason for that is because we are trying to produce 1 mole of a substance. So we only want 1 mole of CH3OH, which means that takes precedent over having whole number coefficients. So we are using this as our basic equation showing the standard enthalpy of formation. So hopefully that's a little better. Let's move on to B. The reaction below is used in the manufacture of methanol. Determine the average bond enthalpy, define the term average bond enthalpy, and using values from table 11 from the data booklet, calculate the enthalpy change for this reaction. So the average bond enthalpy, and let's see, I'll probably write it right above, is just the energy or enthalpy required to break 1 mole. Again, we're still doing 1 mole of elements. 1 mole of a, sorry, I should rephrase this. 1 mole of a bond between elements. And that's usually to produce, so we usually produce 2 gaseous elements. So I'm going to look at table 11 real quick and just pick like bromine. So bromine standard state is Br2. So if we have a mole of bonds, that means 1 mole of Br2. To break every single one of those bonds, it will take 193 kilojoules. And this just makes sense because the units are kilojoules per mole. Anyways, let's go ahead to B. So the second part is using these values, calculate the enthalpy change for this reaction. Another way to show this is that delta H, so the enthalpy change, we can usually do that just to mean standard, is equal to the sum of the enthalpy of the bond enthalpy. I'm going to just do BE to abbreviate bond enthalpy of reactants, minus the sum of the bond enthalpy of products. So to do this math right here, we know that CO2 has 2 C double bond O bonds. We know that 3H2 has 3 H single bond H bonds. So we're going to add those up. Then we are going to subtract the 3 C single bond H bonds plus 1 C single bond O bond plus 1 O single bond H bond plus 2 O single bond H bonds. So we got to do all this math. It's honestly not too bad. It's just a plug and chug of these values. So our C double bond O is going to be 804. Our C single bond O is, let me just go ahead and highlight all these values. We have C single bond H. We have O single bond H. We have O single bond C. And I think that might be it. Oh, and H single bond H. So we're going to be using all these values and we're going to add them together. I'm going to do the quick math. All right, so I just kind of pause it and put some numbers in. If we do this math and we bring all these numbers up, we're going to end up with a total of minus 73 kilojoules per mole. All right. So that's that first answer. So now we move on to the second one. C, one industrial method of manufacturing ethanoic acid uses methanol as a feedstock in the following exothermic reaction. One quick thing I want to note is this has a little front arrow, back arrow. We're going to learn about that in equilibrium. That basically means that the reaction can go both ways, which you'll learn soon enough. All chemical reactions can go both ways, just happens at certain rates. So with this, we are given the standard enthalpy of formation, HF, of a gaseous carbon monoxide. So to produce this gaseous carbon monoxide right here is going to be minus 110.5 kilojoules per mole. Using this information in table 12 from the data booklet, calculate the enthalpy change for the reaction above. So for this reaction, we actually have to use our enthalpy of formation or delta HF equation, which is a little different than the delta H delta H of the bond energy equation. Normally we did reactants minus products when we're doing bond enthalpy, but now we're doing delta H of formation. So instead we're actually going to do the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Which is why we have to look up some of these values. So if I go ahead and I look this right here up, ethanoic acid, I find that the delta H for ethanoic acid is actually negative 484 kilojoules per mole. So I'm going to take that, and then I'm going to subtract the delta HF of methanol. So if I look that up in the data booklet, I find that that's negative 239. And I add that to our negative 110.5 that we were given from the instructions right here. And just with simple addition, keep track of your negatives. You know, this negative is going to turn that positive, and this negative is going to turn that positive, or whatever. So you're just taking a negative number, adding positive number in the end. And so we're going to get a total of negative 134.5 kilojoules per mole. And so our delta HF is that. And so that gets us number 7. Moving straight on to question 8. So once again, I'm going to read the question and then go straight through it. The trend in boiling points for the hydrides of group 15 is shown in the graph below. Discuss the reasons for the variation in boiling point of this series of compounds. And we need to be very careful to look at what the compounds. We have ammonia, we have phosphorus trihydride, we have acetylene trihydride, and we have antimony trihydride. So we have to figure out why they have different boiling points, with ammonia having the second highest. So when we talk about boiling points, generally the one thing we want to pay closest attention to is intermolecular forces. This is all going to be about IMFs, intermolecular force. So when I look at these 3 compounds, I notice one thing in particular. I notice a trend of 3 and 1 not. And when we look down our periodic table, in the same column we have nitrogen, then phosphorus, then As, then Sb. And so as we go through this, I notice that the elements are getting larger, which means the molar mass or the atomic mass, the number of electrons within this is also increasing. So I believe that I can explain this trend right here by an increase in electrons, specifically in number of electrons. Therefore, this is explained by an increase in London dispersion forces. Now, if London dispersion forces have this much of an influence as we increase in number of electrons, the question then becomes, well, what happened to ammonia? Why is ammonia, NH3, have such a higher boiling point when it should have the lowest? According to the trend, it should be like minus 120 or something, but it's not. It's minus 40 or minus 35. And this is because ammonia is special. Ammonia has nitrogen bonded to hydrogen, and therefore it has hydrogen bonding. Therefore, meaning it has higher intermolecular forces than we would expect, and therefore higher boiling point than expected. It doesn't follow the trend of the other hydrides. So moving on to B, explain using diagrams why NO2 is a polar molecule, but CO2 is a non-polar molecule. And it specifies that we must use diagrams. So we're going to have to go ahead and draw this out. So we have to follow our general scheme of drawing this out. So I'm going to go ahead and draw 1, 2, 3, 4, 5. Oxygen with 1, 2, 3, 4, 5, 6. And another oxygen with 1, 2, 3, 4, 5, and 6. So when I look at this, I can automatically assume that we're just going to have a nice little double bond there. And unfortunately, we don't have such a nice bonding angle right here. Now, NO2 does this really weird thing where this oxygen right here, it's going to actually use that weird oxygen rule that it does, and it's going to go ahead and just shift one of its electrons over. And then it's going to kind of latch on right here to this. And we end up with this structure that kind of looks like N single bond O, double bond O, with nitrogen actually unhappy with 1 unpaired electron and only 7. So it's not even fulfilling the octet rule. But that's okay for now. We just need to look at this. CO2 looks like that. And here's where the key points come from this. The key points come from this equation by noting that NO2 is unsymmetrical, while CO2 is symmetrical. Now you could be talking about symmetrical or unsymmetrical in either shape or distribution of charge. And either way, you'll get the marks because both of them show that CO2 will be nonpolar while NO2 will be polar. So if you get the diagrams and you show that they're symmetrical or asymmetrical, and that's the main difference, that'll get you the points. If you don't have the diagrams, you're only going to lose 1 mark on this one. So you don't have to worry too much, but the big points come in right here where you say unsymmetrical or symmetrical distribution of shape and charge. All right. So the last thing, now this is just pure memorization. Describe the structure and bonding in SiO2. SiO2, silicon dioxide, is something very common that you see a lot. This is just, oops, that's not the right letter. This is usually what you think of when you think of like glass, silicon dioxide, sands, rocks. We use that a lot. So all you really need to just say is that this is a network covalent, a giant covalent. Either of those will work. Either of those will get you the points. Some other words you could say is macromolecular, or even repeating. It's repeating tetrahedral. Each one of these works. And then lastly, it said describe, that was our structure. So now we need the bonding. The bonding is single bonds. And you can kind of make sense of that because silicon is going to bond to 2 oxygens, but it's also going to bond to the 2 oxygens of the neighboring ones. These kind of make this really weird shape where we have our silicon bonded to 1 oxygen, but neither are happy, but that's okay because this silicon's bonded to those, which is bonded to another 2, and so on and so forth. This is bonded to an SiO, and it just gets this wild shape. So it is quite cool, but it's single bonds. It is going to be network covalent, giant covalent, macromolecule, or repeating tetrahedral. So moving on to question 9. The use of airbags in motor vehicles is now mandatory in many countries all over the world. Airbags employ a chemical reaction in which solid sodium azide reacts to produce solid sodium and gaseous nitrogen. They literally tell us solid sodium and gaseous nitrogen. So for A, write a balanced chemical equation including state symbols. Well, we know that we start with NaN3, which is solid, is going to react to produce solid sodium, Na, solid, plus gaseous nitrogen, N2, because it's diatomic, gas. Now the only thing left to do is balance. A quick balance shows me that because I have a 2 here and a 3 here, I can do 2, 3 with a 2 on the Na, and we are done. That is 2 marks. 1 for getting it, 1 for balance. Next, an airbag that is made that uses 150 grams of sodium azide. I'm going to write my given, underline it so I know it's there. Determine the amount in moles of sodium azide used in the airbag. Well, I start with 150 grams. Sorry, I need to keep my sig figs. 0.0 grams of NaN3, and I am converting to some amount of mole of NaN3. Well, when I need to convert from grams to mole, I can think of 2 things. One, I know that I'm going to drop it like it's hot. So on the bottom over here, I'm going to have grams NaN3. And I know I want to get to mole, so I'm going to have mole NaN3. And so the question then goes, what's in my brackets? Well, when converting from grams to moles, we are going to use the molar mass. So we just have to add up the individual components of this. So when we add up 1 sodium plus 3 nitrogen, we get a total mass of 65.02 grams. And so I'm going to put 65.02 grams to 1 mole. So that's just 3 times 14.01 plus 22.99. And you add that up, and that's how you get the molar mass. When you then do this math, let's cancel out our units. Grams of sodium azide, 150.0 divided by 65.02. And we are going to get about 2.307. You'll notice I have 4 sig figs because I have 1, 2, 3, 4 sig figs. 1, 2, 3, 4 sig figs. The lowest number of significant figures is 4, so that is what I will use in my answer. Next, determine the amount of mole in nitrogen gas produced when 150 grams of sodium azide reacts completely. So we just get to start with 2.307 mole NaN3. This just carries over. Now we are converting mole of NaN3, which I drop it like it's hot, and we are converting to mole of N2. Well, this time it's not going to be 1. It's not as simple. We have to use the mole ratio from our balanced chemical equation. I notice that I have 2 moles of NaN3, and I see that right here. And for that, I produce 3 moles of N2. My units will cancel out, mole of NaN3, mole of NaN3, and I will get just a nice answer of, got to calculate this really quickly, 3.461 mole of N2. And you can keep the state symbol, gas. And so once again, I'm going to have 4 significant figures. And the reason that I don't use 1 significant figures for these middle guys is they are exact numbers. There's no uncertainty. Significant figures, once again, only comes in as part of our uncertainty, but a ratio, a 1-to-1, is exactly 1-to-1 always. It is not 1.00001 to 1. It's just 1 and 1. Lastly, we have to calculate the volume in decimeters cubed of nitrogen gas produced in this reaction at STP. To do that, you may have to look back at your data booklet because you do need to know that for our volume, we have to know that for our volume, 1 mole, 1 mole of an ideal gas is equal to 22.7 decimeters cubed, or we can use PV equals nRT, which we haven't really learned yet. So I'm just going to stick to our amount of nitrogen, 3.461 times 22.7. Now, when I do this, I get a total of 78.6. It's 78.5, 78.6. You can usually be okay with either of those. It's close enough. The one thing I just want to do is let you know why I did that one more time. It's 3.461 mole. And again, I'm just doing stoichiometry. I know that 1 mole is equal to 22.7 decimeters cubed. Mole cancels with mole, and that's how I get that math right there, decimeters cubed. All right. Lastly, this is a question that you physically cannot answer because we haven't talked about it, but I will give you the answer to this anyways. Nitrogen gas deviates from an ideal gas behavior under certain conditions. State and explain the conditions under which nitrogen gas deviates from ideal behavior. Well, this is true for almost all gases, that if we're at really high temperature, it stops being ideal. Ooh, sorry. I have this one wrong. Not really high temperature. That's my bad. Really high pressure, it stops being ideal. And very low temperature, it also stops being ideal. And honestly, this actually makes sense. All molecules have these intermolecular forces, whether they be London dispersion forces, hydrogen bonding, or dipoles. And the higher the pressure and the lower the temperature, the closer these molecules can get. And if they get close, they start becoming liquid. And if they get close and they have low energy, like low temperature energy, they can start get attracting the way that particles do. And so they stop behaving like a gas and start behaving like a liquid. So that's why we don't want high pressure and low temperature. So we'll worry about that more when we get to gas laws. For now, we'll just move on to our last and final question, question 10, straight stoichiometry. So the reduction of iron ore, hematite, takes place in a blast furnace for the extraction of iron. The equation for the reaction is 2 Fe2O3 solid plus 3 carbon turns into 4 iron plus 3 carbon dioxide gas. A mixture of 30 kilograms of iron oxide and 5 kilograms of coke, assume that coke is pure carbon, was heated until no further reaction took place. Coke is not a drug or a soda. Coke is a fuel that is a high carbon content. And in this problem, we are assuming that Coke is pure carbon. Once again, we are assuming that Coke is pure carbon. It is also used as a reducing agent in a blast furnace. So A, calculate the maximum mass of iron that can be obtained from this reaction mixture. Give your answer to 3 significant figures. So from this mixture, we have to find the maximum amount of iron. The first part is we need to figure out how much iron we can produce from either the carbon or the iron oxide, because one of them is very likely our limiting reagent. So we're actually going to do it for both. And I'm going to spend this extra space down here. So starting with 30.0, whoops, starting with 30.0 times 10 to the third grams. You'll notice I immediately converted to grams, not kilograms. And the reason for that is our molar mass is in grams, not kilograms. And I'm trying to convert to moles. When we do stoichiometry, we are trying to convert to moles. When you do almost anything, try and convert to moles. So of Fe2O3, and we're going to convert that into, like I said, moles. And specifically, we're going to convert that into moles of Fe2O3. So I'm going to be a little more specific. Mole Fe2O3 from grams of Fe2O3. And we know that we're going to use the molar mass, so it's 1 mole. And so the molar mass of Fe2O3 is the mass of 2 irons plus 3 oxygens. That's going to be 55.85 for the iron times 2 plus 16.00 times 3 for the oxygen, which gives us a total of 159.7. So I'm going to put that right here, 159.7. And that gives us moles of iron oxide. However, the question is asking for calculate the maximum mass of iron that can be obtained. So what I want to do is actually go to iron. Now, I'm only going to go from mole of iron oxide to mole of iron, and our units will cancel out here. And the reason I'm not going all the way to mass is because if it turns out that we're not going to use iron oxide as the limiting reactant, I don't want to do the extra step. So I'm going to stop at moles regardless. Using our balance equation, it is 2 moles of iron oxide to 4 moles of iron, which honestly just simplifies to 2 over 1. And so I'm going to go ahead and do this math right here. 30.0 times 10 to the third divided by 159.7 times 2 is going to be a mass, or sorry, be a mole of about 376 mole of iron produced. All right, that's a lot of iron. So now we have to do the same thing for carbon, starting with 5 kilograms of coke. So 5.00 times 10 to the third grams of carbon. Now carbon's a bit easier. I know that's 12.01, no math needed, grams of carbon per 1 mole of carbon. Then we're going to do mole of carbon to mole of iron. Again, I have to go up and look. That is a 4 on the top, a 3 on the bottom. And when I go ahead and work out this math, I end up with, let's see. So I end up with about 555 mole of iron. All right. So looking at both of these, I know that my limiting reactant is the one that produces less. So therefore, the maximum amount of iron I can make is 376 moles. So I'm going to go ahead and write 376 mole of iron. The last thing is we need the mass. Mole is not mass, so we need grams. So we just have to do a final conversion. 1 mole of iron is equal to 55.85 grams of iron. I got that from both the periodic table, but also we used it earlier when we were calculating the mass of iron oxide. And so doing this out, I get a whopping, I get a whopping 20,999.6 grams. Now, the problem is we need 3 significant figures. And also, just for clarity's sake, I assume they want it in kilograms because that's what everything else was given. So I could just write 2.00. Oh, this one didn't even work out. I need to convert to scientific notation. I could do it like this. 2.0 times 10 to the 1, 2, 3, 4 times 10 to the 4th grams. Oh, sorry, I even got that one wrong. Shouldn't be 2.00. It should be 2.10 because we have to round up grams, or I can make it a lot nicer and just write 21.0 kilograms of iron. So there is our long and drawn out stoichiometry to get 21 kilograms of iron. All right, we are on the last question of the last question, and then we are done. So I'm going to go ahead and actually move all this stuff down because I don't want to look at it for a bit. The actual yield of iron was 14 kilograms. Calculate the percent yield of iron. Well, I know that my percent yield, spelled right there and I still got it wrong, is my actual over my theoretical times 100, which just means 14.0 divided by 21.0, which is going to be equal to 2/3 when we divide them both by 7, which is going to be equal to 0.67, or sorry, we need 36667, and then times 100 to get our percent. It's going to be 66.7% yield. Easy peasy, lemon squeezy. That's going to be the last of it. And so hopefully this all makes sense. If it doesn't, rewatch it. Have a good night. Have a good weekend. And I'll see you all soon for your paper 2.